We've looked at salt solutions, and now we can start looking at salts of polyprotic acids. These can also affect the pH of a solution if you have a pH-active species. So let's look at the example of a salt containing the carbonate ion. At first glance, you'd think, well, the carbonate ion comes from carbonic acid, and it does, but it really comes from the hydrogen carbonate ion, which is the second ionization of carbonic acid. So when we have a conjugate acid of the conjugate acid of the, or the conjugate base of the conjugate acid of the conjugate base of the weak acid originally, then you can get two equilibria, and it gets kind of crazy. So we get two basic equilibria going instead of two acid equilibria going. So the carbonate ion can react with water to produce the hydrogen carbonate ion. And now the hydrogen carbonate ion, which is the conjugate base of the weak acid carbonic acid, can react with water to give us carbonic acid. So when we look at this, we say, okay, this -2 ion, the carbonate ion, has this Kb value. Kb, this is Kb1 because it is equal to the hydrogen carbonate ion divided by the carbonate ion concentration times water. But we don't put water in there, do we? Right? Plus hydroxide. God, I'm really slipping. So, times the hydroxide concentration divided by the carbonate concentration. And over here, we have Kb2, which is equal to the carbonic acid concentration times the hydroxide concentration divided by my hydrogen carbonate ion concentration. Now, we call this Kb1 because the carbonate is getting the first proton back, right? It's acting like the base the first time. Now, this can also act like a base to get the second proton back, so we call this Kb2. Now, when we think about these are conjugate bases. So when we need a Kb for a conjugate base of a weak acid, where do we get it? From the Ka. So when I start to think about this, let's go back to carbonic acid and look at its two equilibria. I'm flipping back to page 1638. Here are the two equilibria for carbonic acid. The first one, which had the Ka1, has carbonic acid in equilibrium with a proton and a hydrogen carbonate ion. Ka2 represented the hydrogen carbonate ion in equilibrium with the proton plus the carbonate ion. So now let's look at my Kb1. I have a carbonate ion and a hydrogen carbonate ion. Which Ka has those same species? 1 or 2? 2. So these two species that are in my Kb expression come from Ka2. So for a diprotic acid and its conjugates, Kb1 is equal to Kw divided by Ka2 from the acid. Does that make sense? That's really important. And the reason I know that is because these two species were in the second acid ionization. Now, this is my second basic ionization, and it has a hydrogen carbonate and a carbonic acid. So I look for those two species, the acid-base conjugate pair, and that came from Ka1. So Kb2 is equal to Kw over Ka1. So again, this gets a little messy, right? I know some of you are still struggling with the whole salt thing from a weak acid. Now we have two possible salt ions, and so we have two equilibria. So my Kb1, we can find it. It's equal to Kw, which is 1 times 10 to the negative 14th, divided by Ka2, 4.7 times 10 to the negative 11th. So my Kb1 is 2.1 times 10 to the negative 4th. So when we look at that, what does that tell you about our value of X? It's kind of marginal for can we ignore X. It would depend on concentration. Then my Kb2 is equal to Kw, 1 times 10 to the negative 14th, divided by my Ka1, which was 4.5 times 10 to the negative 7th. So my Kb2 is 2.2 times 10 to the negative 8th. So when I look at that, we say, well, we know that one is really small, so we can ignore Y compared to X, even though we may not be able to ignore X compared to our original concentration. So when we look at this Ka values and the Kb values, regardless of whether we're doing an acid or the conjugates, then we can decide what we can ignore. Okay. How do we use this then in order to find pH? What's the pH of a 0.15 molar solution of sodium carbonate? Well, we said previously that when the second ionization is small compared to the first, if all we're doing is figuring out pH, we don't have to worry about the second ionization. So that's the good news in this mess. Yes? Okay. Let me stop this.